Hello everyone, welcome to my VLSI diary. My name is Shivangi Upadhyay and in this channel we will explore the fascinating world of VLSI design, RTL coding and FPGA implementation. If you are a student, a beginner or someone who is just curious about how tiny chips power big technologies, you are absolutely in the right place. In this channel, I will share everything I have learned from the basic to advanced. So, whether you are preparing for placements or just starting your VLSI journey, these videos will help you step by step. So, let's start with the most basic question. What is VLSI? VLSI stands for Very Large Scale Integration, which means designing integrated circuits that can contain millions or even billions of transistors on a single chip. It's the technology behind everything we use, from smartphones and laptops to IoT devices, car, and even satellites. In the beginning, we had SSI, small scale integration, with just about 10 to 100 of transistors, which forming simple logic gates. And then come the MSI, medium scale integration, packing hundreds to a thousand of transistors to create components like adders and multiplexer. And then next was LSI, large scale integration, jumping to thousands of transistors enough to build small memories or microprocessor. And today we are in the VLSI era, where a single chip can hold billions of transistors, powering everything from smartphones to supercomputers. In short, from SSI to VLSI, we have moved from basic logic to complete system on a chip. VLSI replaced all of these, allowing us to build complex multifunctional chips that can perform multiple operations on one tiny silicon wafer. It brings together digital, analog, and even mixed signal circuits all inside a single chip. Because of VLSI, we can now design systems that are smaller in size, faster in speed, consume less power, and are much more reliable. Some common examples of VLSI-based system includes microprocessors, GPUs, SoCs, and ASICs, basically the brain behind every electronic device we use today. So that's what VLSI is, the technology that powers the modern digital world. Now that we know what VLSI is, let's talk about why we actually need it. The main reason is to make our electronic systems more efficient and powerful. VLSI helps us increase the efficiency of an IC or a chip by integrating all the required components into a single design. Instead of using multiple separate chips for different tasks, we can design a single system on chip that performs everything, which makes the system faster, smaller, and more reliable. It also ensures low power consumption, high circuit density, and faster processing speed, all of which are essential for today's devices like smartphones, laptops, and wearables. Another big advantage is miniaturization, which is packing more performance into a smaller space while keeping the cost low. That's what makes VLSI the core of modern electronics. And finally, VLSI enables parallel processing power, which is the reason behind technologies like multi-core processors and GPUs that can perform thousands of operations at the same time. So, in short, we need VLSI because it's what makes our electronic world faster, smarter, and more compact. That's why it's one of the most exciting and in-demand field in electronics today. Before we dive deeper into VLSI, let's first understand the basic foundation. you need to get started. At the core, everything begins with the logic gates like AND, OR, NOT, NAND, NOR, XOR, XNOR. These are the fundamental building blocks of digital circuits. Then comes combinational logic, where we design circuits like adders, subtractors, mux, demux, comparators, code converters, ALUs, and even 7-segment decoders, all working without any memory element. Next, we move to the sequential logic, which adds memory into the picture. Using flip-flops, latches, registers, counters, we also explore finite state machines, memory units, clocked sequential circuits, and programmable logic devices like PLDs. You will also need a solid grasp of timing concepts like setup time, hold time, clocking, and understanding metastability to ensure reliable circuit operations. And finally, Boolean algebra and K-map simplification are essential to optimize your digital design and make them more efficient. So, mastering these basics give you the perfect foundation to move into RTL design and advanced VLSI concepts. Now that we know the basics, let's talk about how we actually describe hardware using hardware description language or HDLs. In VLSI world, the most common one is Verilog HDL, widely used in the industry for digital design. Then we have System Verilog, which extends the Verilog and is mainly used for verification. This is where we build drivers, monitors, scoreboards, and agents using System Verilog classes and interfaces. For advanced verification, there is UVM, the Universal Verification Methodology, perfect for the complex chip verification and emulation. Another important one is VHDL. It's important in defense and aerospace industries, used to model and simulate digital systems, especially for FPGA and ASIC designs. Basically, you describe how your circuit should behave using code, and then synthesis tool converts the description into the actual logic gates and hardware. Pretty cool, right? In VLSI, there are mainly two design methodologies. One is ASIC and another is FPGA. ASIC stands for Application Specific Integrated Circuit, is a customized chip made for a particular purpose or a specific purpose. It offers high performance and low power consumption, but once it's fabricated, you can't change. It is fixed. On the other hand, FPGA, which stands for Field Programmable Gate Array. This is reprogrammable, which means you can modify or update the design anytime. It's great for prototyping, low cost development, and flexibility. So, both ASIC and FPGA use the same HDL design, but the difference lies in what happens afterward. For ASIC, the design goes to a foundry for fabrication, and for FPGA, it's simply loaded as a bit stream into the chip. That's how these two methodologies shape how real world chips are built and tested. We are going to explore the complete VLSI design flow. Basically, how a chip is designed step by step from an idea all the way to implementation. Everything starts with the design specification. This is where we define what the chip needs to do, its functionality, power limit, and performance goals. Next come behavioral specification. Here we describe how the chip should behave logically, usually using flowcharts and algorithms. Then we move to the RTL design, written in HDLs like Verilog or VHDL. This is where the actual digital logic of a circuit is described. After coding, we do the functional verification to make sure the design behaves as expected before moving forward. Then comes the logic synthesis, where the RTL code is converted into gate level netlist using standard cells from the library. The gate level netlist represents the entire design using logic gates and interconnections. It's like the blueprint of the hardware. Here we do another round of verification to check that the synthesized gate level design still works correctly. No surprises at all. Now it's time for physical design. We perform floor planning, placement, and routing to design where each component will physically go on the chip. This gives us the physical layout, which shows the actual geometries that will be fabricated on a silicon. Before sending it off, we do the layout verification, checking for a design rule verification and ensuring that the layout matches the schematic. And finally, implementation. This is where the design is fabricated into an actual silicon chip. From code to hardware, that's a full VLSI design journey. Now, let's look at the design flow for ASIC and FPGA. Even though both ASIC and FPGA design flows starts with similar steps, the final outcomes and processes differ significantly. Both begins with the design specification, where we define what the system should do, followed by the RTL design, written using SGL languages like Verilog and BSGL. Next comes functional simulation, where we test whether our design logic works as expected before any synthesis. After verification, we move to synthesis, which converts the RTL code into a gate level representation. Now, this is where the design diverges. For FPGA, we perform place and routing directly on the FPGA fabric, followed by bit stream generation. The bit stream file is what gets programmed into a FPGA device. In contrast, for ASIC, the flow continues with backend place and route, followed by the sign-off steps such as static timing analysis, design rule check, layout versus schematic. Finally, for FPGA, we program the chip and can reconfigure it anytime. Whereas in ASIC, the design is sent for fabrication, producing the final silicon chip. So, while both starts with HDL and verification, FPGA is flexible and reprogrammable, and ASIC is permanent but highly optimized for performance and power. Now, let's move on the fabrication process, which happens at the silicon level, the stage where our design becomes a real chip. It all starts with mask creation, which act like a stencil or a blueprint to define the circuit pattern. Next, lithography, which transfers the mask pattern onto a silicon wafer. Then comes etching, where the unwanted material is removed to carve out the desired structure. After that, doping modifies the electrical properties of silicon to form transistor. In metallization, conductive paths are added to the contact different circuits element. Finally, packaging seals and protects the chip while making it ready to connect with external circuits. And that's how we end up with the fully functional silicon chip ready to be mounted on a PCB. Now that our chip design is complete, the next major step is verification and testing, one of the most critical part of the VLSI flow. Verification ensures that the design works correctly or exactly as intended before fabrication, and testing checks it after the chip is made. First, we have functional verification. This is where we simulate the design using test benches to check if behaves correctly under different inputs and scenarios. Next is formal verification. Instead of running simulation, this uses mathematical proofs to verify that the design meets all specification logically. Finally, we have DFT, design for testability. This step adds extra logic like scan chains so that after fabrication we can test the internal circuits of the chip easily. So, verification makes sure our design is correct before manufacturing, and testing ensures that the fabrication chip works perfectly in the real world. Now that we have understood how VLSI design and verification works, let's look at the career opportunities and applications in this field. Front-end engineers focus on RTL design, synthesis and verification. This is where you describe how the circuit behaves using Verilog or VHDL. And then back-end engineers work on physical design. They handle layout timing and check like DRC and LBS to make sure the chip can be fabricated correctly. And then DFT engineers or design for test engineers ensures that chip can be tested effectively after fabrication by inserting scan chains and test structures. After that, verification engineers plays a crucial role in simulation, assertion and coverage. They ensures the design works exactly as intended before it's taped out. And then analog engineers deal with the circuits like op-amp, ADCs, DACs, and PLLs. These are essential for signal processing and communication systems. And finally, CAD engineers develop automation tools using scripting language like TCL, Perl, or Python scripting. They make the design flow faster and more efficient. So, whether your interest lies in digital logics, analog design, testing, and automation, PLSI offers a wide range of career paths for every kind of engineer. So, let's wrap up everything we have learned so far about the world of PLSI. First, beginner level. Start your journey by mastering digital electronics and SGL basics. After that, intermediate level. Move on to the Verilog coding, simulation, and synthesis. After that, advanced level. Dive deeper into physical design, static timing analysis, design for test, and low power design techniques. And then expert level. Finally, step into SOC design verification, debugging, mastering EDA tools. Remember, VLSI is not just a science, it's an art of designing electronic brains. You start by writing HDL, simulate it on an FPGA, move to the ASIC flow, and one day you will be fabricating your own chip. If you are excited to learn VLSI in simple and practical way, make sure to like this video, subscribe to the channel and turn on the bell icon so you don't miss any of our upcoming lessons. I am so happy to have you here. Let's start this amazing journey together. Happy learning!